Okay, our first one is going to be taking a look at the pressure of gas solute and solubility of the gas solute. Okay, here we have Mason Howard squeezing the unopened bottle of seltzer water. Go ahead, Mason, squeeze. The bottle is very firm because, now Mason, point at the space in the little air there. The air, or the gas above the liquid, is at a very high pressure in an unopened bottle of seltzer water. Okay. We're now going to take a look at, we have the unopened room temperature bottle of seltzer water. Mason's going to open the bottle. Now what we see is bubbles formed inside the water. Mason's hand got soaked and liquid came rushing out of the top of the bottle. We heard a little sound of CO2 gas leaving the container. What this is demonstrating is as the pressure of the gas on top of the liquid becomes less when the gas rushes out of the container when Mason opened it. When the pressure above the liquid becomes less, the solubility of the gaseous solute in the solvent, which is water, becomes less. The evidence of that is the CO2 bubbles forming in the water and rushing out of the solution. Pull the board a little bit that way, Mason. Okay, our next part of the lab, we're going to take a look at temperature of solution and solubility of a gaseous solute. Thank you, Mason. Mason's now going to open up a chilled, cold bottle of seltzer water. Now, if we focus on the seltzer water, we can see that the cold water met much less amount of bubbles formed when the lid was open, which indicates that more CO2 is staying in the solution, and the CO2 is then more soluble when the temperature of the solution is lower. Okay. Now Mason is going to demonstrate, again, the influence of temperature on the solubility of a gaseous solute. In the beaker is the carbon dioxide water solution, seltzer water. Mason is heating a nail in the Bunsen burner flame. We're going to take the nail and insert it into the solution and watch what happens right at the surface of the nail. Now if we can look, we can see bubbles forming on the surface of the hot nail. The bubbles forming indicates that the CO2 is leaving the solution, meaning the CO2 is now less soluble at the higher temperature near the nail. So with a gaseous solute, as temperature goes up, it becomes less soluble. As temperature goes down, it is more soluble. Thank you again, Mason.
I want to make sure it covers it up.
The next concept we're going to take a look at is something known as miscibility. This would be something we're familiar with for all that have had Italian salad dressing. Oil and vinegar separate from each other. It's a concept known as like dissolves like. Polar things tend to dissolve in things that are polar. Non-polar tend to dissolve in things that are non-polar. With Italian salad dressing, oil is non-polar, so it separates from the polar water. If two things can mix together, they're known as miscible. Something like oil and vinegar would be immiscible. They cannot mix together.
Water's on top, right?
Don't know. Now here in a beaker, which Mason is pointing at, we have water and hexane. Hexane is nonpolar, water is polar. At this point in time, we do not know which layer is which. So we're going to add something to our mixture. We're going to add iodine crystals. Okay, what we now have is we've placed some elemental iodine, which is I2 and nonpolar crystals, into this mix of the hexane and water to try to determine which layer is hexane. Iodine, because it's nonpolar, should dissolve in the hexane layer. Stir away, Mason. Vigorous, vigorous. Now if Mason pauses, we can see the upper layer becoming purple, which would indicate that iodine is dissolving in the hexane. So in this circumstance, we found that the upper layer is the hexane, the lower layer is the water. Okay, now we're going to add a drop of green food coloring to the beaker. And Mason's going to stir again. And now we see that the green food coloring dissolves into the water layer, which tells us that food coloring is polar because it's mixed with the polar water. The iodine is nonpolar, so it mixed with the hexane layer, making the hexane purple-pink. And we can see that like dissolves in like, or miscibility.
It's like a mock version.
The last demonstration is a concept called supersaturation. Supersaturation is a circumstance when more solute is in the solution than should be at a given temperature. The solution was created by warming it up to a high temperature, dissolving an excess amount of solid solute. The solution was allowed to cool to room temperature, and rather than reforming as crystals, the extra solute stayed in solution, making the solution what we call supersaturated. Now, Mason has in his hand a test tube of sodium acetate that is supersaturated. Robert's going to come in from the side and add what's called a seed crystal to the solution. Robert adds this. What we can see, starting at the top of the test tube, is the excess crystals are now coming out of solution and reforming solid. The excess crystals are the solute that should not be in solution at this temperature, which made the solution supersaturated. They're now all rushing out of solution to return the solution to what we would consider a saturated state. Now, if Mason were to feel the test tube is hot. Energy had to go in to make the solid dissolve, so as the solid comes out of solution, energy is released back out, making the test tube hot.